All right, so as mentioned in the last video, we're going to transform this top-level schematic into a couple of sub-schematics that we can use in order to do the layout more effectively. So here you can see I've taken this matching network and I've transferred it over to this schematic, and I've just called this schematic class APA underscore MNW for matching network. I might have called it OMNW for output matching network if I was going to work on both an input and an output matching network. But for the time being, we're just doing the output matching network. Now, in order to make this schematic more readable, I've spread the components out a little bit. And so you can see that the network is more or less the same. I've got my supply pin coming into one inductor. I've got the signal path going out through a capacitor network going to the output. And I've got a VSS pin so that I have grounds for all the different signals. And then finally, I did have to add one extra pin that is going to go towards the PA, and I've just labeled that one PA. Now, I'm working with all in-out directional pins. For the time being, I just find them a bit easier to label things that way, since really it's not clear that all these things are not input outputs. There's current going in both directions, but you can label things clearly as input or output if you prefer. It doesn't really change anything. All right, so let's take the schematic that we created for the matching network, and we're going to launch Layout Excel. We're going to create a new one, and we'll have the configuration be automatic. All right. So now it's created a layout from the schematic, and this layout is going to be empty for the time being. We're going to go to this Generate All from Source icon in the bottom left-hand corner of the window, and we can do some things like move the pin layers around. For instance, right now I want all of my pin layers to be on an upper metal layer, so I'm going to make that change. For the time being, I think I can leave almost everything else as fixed. All right, now what you can see is that it brought in, it's obvious it brought in a couple of inductors. Those are very big. If we highlight, you'll also see that it brought in our capacitors. We can zoom in and see those capacitors right here. All right, so the name of the game is we want to move this around while minimizing the amount of excess routing that we have to do, because this design is being done at 5 gigahertz, and any interconnect that we put in is going to have to be modeled. Now, this is not necessarily the way that I would design this matching network. I would probably spend a lot more time optimizing the coils or maybe using a transformer, because with two coils of this size that are going to be very close to one another, it's going to be difficult to keep the coupling from affecting the design, and that hasn't been taken into account in the schematic level design. So normally we're going to have to iterate a couple of times on this by doing an EM simulation with all the coils in the design. And then iterate back towards a complete design. I can also do things like this particular PDK does have transmission line-based components, so I can model the interconnect between, say, this inductor and this inductor more effectively and iterate in that manner as well. But what is going to be difficult is to catch the coupling factor, the magnetic coupling factor between this spiral and this spiral. That has to have an EM simulation in order to do that. All right, so I'm going to manipulate this layout, and in the next video, I will show you the net result after the manipulation, and then we will run through our checks to see how this turned out, whether the DRC checks are met and whether the LVS checks are met.